Okay, we should get started. I think everybody got their stuff back. And while this isn't really the lab, a lot of you forgot to do the last two pages in the lab. If you want to turn that in ASAP by next week, that's fine with me. I think maybe it's because I handed out only partial packets and not the whole thing. Anyway. So don't forget to turn in the homework, the written homework that was due today later at some point. And we have a quiz coming up on Wednesday. That is going to cover, I think, pretty much Coulomb's law. Like maybe some covalent naming, stuff we did that wasn't on the last quiz. But, everything from last week, Coulomb's law stuff. So we'll stick with the light. I think I'll verify, but I think we're going to stick with the light stuff for the next quiz. But Coulomb's law is a big part of the quiz this week. Okay, let's see what else. It's the new mask. If I sound too muffled, if you can't hear anything, let me know. It's a little safer for everybody. It seals better, and it's more comfortable. It looks crazier, but it's actually more comfortable. It's got like a gel thing. So anyway, all right. So it feels like it's been a long time. So let's review a little bit. So the whole point, I think we left off with talking about light, just measuring light. And again, the reason we're doing all this is we are trying to expand on this current model of the atom. So we know that there's a nucleus that has protons and neutrons, and that's where most of the mass of the atom is. The nucleus is so much smaller than the rest of the atom. The rest of the atom is empty space. That empty space is occupied by the electrons, but that's it. We don't really know much about what the electrons are doing. And so we want to know, how are the electrons distributed around the nucleus? Is it random or is it not so random? And so we're gonna interact matter with light to kind of see what happens. And that's what we're going to do. We're going to see a bunch of raw data, and we're going to start trying to interpret the data. We're trying to see what kind of patterns we see, and then come up with a model of an atom that will fit the data. And so we're going to build up into the quantum mechanical model of the atom eventually, ourselves. We're going to have a lot of help. We're going to just tell you what parts are important, and you're not going to do the experiment yourself. But we're going to come to the same conclusions that a lot of these famous people came up with. So I was going to switch to this. This is a photo from 1927, and it's got like so many famous people in it. And this is a physics conference, not even chemistry, and I know like more than half of these people. So this guy here, Niels Bohr, we're going to see his model of the atom. We're going to look at something called the Bohr equation. Of course, everybody knows Einstein. We're going to see something he did this lecture, the photoelectric effect, explained it. De Broglie, Born, there's so many people. Fowler. A lot of campuses across the country have buildings named after this guy. I think this is the Pauli exclusion principle, guys. You probably heard of that. Schrödinger's equation. Tons of them. Bragg, Dirac, Marie Curie, Max Planck, or Planck's constant. That's him. Langmuir. There's a journal named after him. Every one of these people are super, super, super famous. Lorentz. There's the Lorentz equations. Anyway. All of this stuff we're going to come up with, we're going to see, came kind of from these guys, which is interesting. Okay. So we are going to, we've already seen how light is measured as a wave. We use wavelength and frequency. We kind of jumped the gun a little bit, and we said, oh, well, you can also measure light as a particle. We can measure the energy of the particle of light, that particle called a photon. And we saw an equation on how to do it. So energy of a photon is equal to Planck's constant times the speed of light, times the frequency. Another version of it is using wavelength. And of course, you can relate frequency and wavelength using the speed of light. Okay. So we've seen all these, I think, right? Yeah, okay. All right. So now that we have the tools in our toolbox to understand what we're seeing, we can get to the real stuff. So just FYI, we've been studying Coulomb's law this last week, and we're going to see it some more. This is the equation we've been working with, where V is potential energy. If you go look it up online, you look it up in other textbooks, you might see Coulomb's law referred to with a slightly different equation. You might see a force rather than a potential energy. And if that's the case, all that changes is instead of just plain distance between the two particles, there is a distance squared. R and D are the same. They call it radius instead of distance, but it's still a length. But these are essentially the same. It's just interpreting it using a energy or a force. And if you are wondering how these work, well, remember that energy is force times distance. So you can do a little rearrangement and plug things in and get one from the other. They're easy to derive. Okay. Did we do this last week? We did. Okay. So we did the ionization energy thing. And yeah, that's right. And we found out that the relationship between the ionization energy and the potential energy was that they were opposite. So you have an attraction between an electron and the nucleus, which is positively charged because of all the protons, and that attraction creates a negative potential energy. The ionization energy, the energy needed to remove an electron, is just the opposite of that. You add that same amount of energy to get that potential energy back to zero. When the potential energy is zero, the electron is no longer attracted. So essentially, it's not attached anymore. So you need to be good at manipulating Coulomb's law. So if the distance changes, what happens to ionization energy or potential energy? So think about it in terms of potential energy first. A closer distance will give us a much lower, more negative potential energy. And so if it has a more negative, much lower potential energy, it'll have a much larger ionization energy. There we go. So slow. You can't click it super fast. So what about if the distances are the same and you change the charge instead? Well, you can see that if you double the charge, the numerator is going to double, and your potential energy is going to double as well, right? It's already negative, so you're doubling a negative, you get a more negative number. So a more negative potential energy, when you have a higher charge, means a higher ionization energy. All right, so a nucleus with a +2 charge, 2 protons, is going to have a higher ionization energy than a nucleus with a +1 charge. And that should make sense to you conceptually. If I've got an electron and it's attracted to a nucleus, it's going to be more attracted to a stronger positive charge than a weaker negative charge. So a nucleus with more protons, that electron is going to get really stuck on that, and it's going to be harder to remove. So you'll need a higher ionization energy to remove it. So real world example, helium plus has 2 protons. And so it's going to have a +2 charge to the nucleus. And so that electron is going to be harder to remove from a helium ion. Why, again, a helium ion? Is because we just want to compare apples to apples. We want to make sure that there's only 1 electron. Right? Helium normally has 2. So if we make it helium plus, then it's a helium that has only 1 electron. I mean, so does this confirm real life? Well, kind of. You haven't had the experience yet, but in chemistry, H plus is all over. You can find it in lots and lots of systems. It's in biology. H plus exists everywhere. It's easy to remove that electron, but you never find helium 2 plus in nature. You can forcibly make it in a lab, but it doesn't really exist in nature. So that just kind of shows you that that electron is extremely difficult to remove. All right, and yeah, we did all this. I think we did all this, yeah. So talking about sizes of ionization energies, what the sign means. So make sure you're reading everything right, okay? Use the correct adjectives, higher versus lower, right? Those will include the sign in the meaning. Lower means more negative. Higher means more positive. Don't use big and small unless you're sure you know what the context is. All right, a big number, you can have a big negative and a big positive, so you can't really tell which way what sign you have. So lower means more negative. Higher, more positive. Okay. All right, that's very review. Now let's go with the more recent review. We talked about electromagnetic radiation. We talked about how to measure it. So the spectrum is a pretty large spectrum. What we can see is only a very small portion of it. And since that portion is easy to describe using nanometers for the wavelength, you're going to get a lot of wavelength measurements in nanometers. But to use this equation or this equation, make sure you plug in your wavelength in just plain meters. All right? Speed of light is meters per second. So your wavelength has to match the units. Energy is joules. Remember that a joule is a kilogram meters squared per second squared. So your wavelength has to be in meters to match the meters in the energy units, okay? Okay. So wavelength, frequency, energy of a photon. These are three things. You just need one of them to understand what kind of light you're looking at. I can give you a wavelength, you should be able to calculate the other two. I can give you energy of a photon, you should be able to calculate the other two. Okay. We covered this. I'll give you the constants. Speed of light, Planck's constant, don't worry, you don't have to memorize those. But you should know, and the equations as well, but you should know how to use them and how to manipulate them. So I could just give you that one and you should know how to do that. All right, we went over this. All good. You don't need to memorize the actual range numbers, but you should know in general what the different regions are called and kind of where they are. Like what's next, kind of the order. Like I said, you don't need to know the range, the actual range boundaries. That's too much. All right, we did do this. Yeah. And did we do this? I don't think we did this one. Okay. So this, I'm not going to turn the clicker on because it's hard to do from your seats. But if you have two waves, predict which wave has the higher frequency. So frequency, that's hard to kind of visually see sometimes. What's easier to see is a wavelength. And how do you measure wavelength? Well, you just literally measure between the peaks. So this one is about 19 centimeters on the screen. This one's about 27 centimeters on the screen. This is a longer wavelength. That is a shorter wavelength. So remember that frequency and wavelength are inversely proportional. One goes up, the other goes down. So the higher frequency is going to be the one with the shorter wavelength. And so that's going to be A, the shorter one we measured. Now, what you might have been looking at, if you got it wrong, was the intensity of the light, the amplitude, how tall the peaks are. That is a measure of intensity, with how bright the light is, which has nothing to do with the color, what kind of wavelength or frequency it is. Actually, it doesn't have anything to do with the energy either, but we'll get to that. So A is more intense. It's more bright. and which one would be more red versus blue. So you kind of have to know the generics of like what the visible spectrum is. So if you think of the visible spectrum with violet and blue over on this side and red over on this side, this is around 350, this is around 800 nanometers for the wavelength. And so a shorter wavelength will give you the more violet-blue region. A higher wavelength is going to be more red. So the more red one should be the higher wavelength, which would be B. The longer wavelength, I should say, because it's a length. And I think I talked about this in my other class, but I don't think I mentioned it to you. If you are one of those people that were never introduced to understanding the colors of the rainbow, one of the ways to kind of memorize the different colors of the visible spectrum is to remember the mnemonic Roy G. Biv. Just think of a person named Roy G. Biv. And that stands for red, orange, yellow, green, blue, indigo, violet. We don't really use indigo anymore, but indigo is a lighter shade of blue. Other way around. Blue is a lighter shade of blue. Indigo is a deeper shade of blue. And then violet is not purple. Violet is kind of a really dark, purplish blue, but still blue kind of thing. Purple is more of a mix between blue and red, which doesn't exist in the rainbow. You have to mix colors to get that. But anyway, so if you remember Roy G. Biv, think of this as low energy, low frequency, high wavelength. And over on this side we've got high energy, low wavelength. And if you can't remember, hey, which side is which, just think about which side is closer to the dangerous part of the spectrum. You guys know ultraviolet. Ultraviolet is bad for you. That's right next to violet. So once you get past violet, ultraviolet, that's when it starts getting bad. That's the high energy stuff. So that helps me remember which side is which. Okay. All right, this is all more stuff. So, yeah, amplitude again. We're not going to focus on it too much, but that only tells you the intensity of the light. That's it. Okay, so which has more energy? I'm going to skip past this good and fast because we're kind of behind. We need to catch up a little bit. A blue light photon is going to have more energy. All right, blue over here. Green is a step in the lower energy direction. So blue is higher energy. This is an interesting question. So UV radiation is more dangerous than visible radiation. Why? UV has a longer wavelength. No, UV has a lower wavelength. UV has a higher frequency. That's true. As you go from this way to this way, you're going to higher frequency. Higher energy is higher frequency. UV travels faster is not true. They all go the same speed, the speed of light. And UV has a greater intensity. That's irrelevant to the color. Anything can have a higher intensity. You just make it brighter, right? You could have really low intensity UV light. You could have high intensity red light. So the intensity is not related to the color, the type of light at all. So that's not a relevant answer, basically. So yeah, it was only B. A is flat out wrong, so B. Which is right there. Okay. So this is a good one. Here, I'll turn the question on for that one. Which of these goes in terms of increasing energy, low to high? So remember the less than sign. The alligator's mouth goes for the bigger one, right? So visually remember which way is which. So most of you said E, and you would be right if you said E. Not quite sure where the A came from, but okay. All right, so let's get into a little bit more specific. So we've kind of focused on the wave part of light quite a bit. We're going to get into light as a particle in a second, but we kind of skipped over the why waves, why particles, like what about it, you know, what gives us the right, you know, why can we describe light as a wave? Well, it turns out if you compare light to simple water waves, you know, you literally get a tank of water, generate waves of a certain shape, and repeat them and see what they do. Well, waves reflect, right? If you bounce them off a wall, they reflect. They'll diffract if you have waves heading. So, like, what you should think of these lines is like where the peak of the wave is, and then in between is where the trough. So think of like the wave cresting on these peaks, where the lines are. Well, anyway, when you have a wave heading towards a wall with a little hole in it, whether it's a water wave or any other kind of wave, as soon as it hits this hole, it'll spread out in all directions. That's called diffraction. Yeah, that's called diffraction. And that's what water waves do. And it turns out light does the same thing. Did I show you the animation of that waves? I think I did. Well, let me pull it up again, because I think I didn't show you the extra one. So, take a second to pull up. So this is a nice little computer demo you can play with to see what waves do. And you'll have to trust that it does the way it does, because this is a computer, but they modeled it pretty well. So first of all, interference, okay? If you have water droplets, each creating a wave that spreads out in concentric circles like this. I mean, you've seen this before if you drop water in a puddle. Well, light does the same thing, but if I have two drops going at the same time, they'll each create their own concentric circles, but those waves will overlap, and they can overlap in two different ways. One is called constructive interference. So if I've got a wave that looks like that, and another wave comes in and overlaps it, like we call this in phase, where the peaks and the troughs match up, then these two will add together and make a really large wave like this. The amplitudes will double. That's constructive interference. But the opposite can happen as well. These waves can overlap and be out of phase. So you have the peaks and the troughs here. Instead, this wave is going to be trough, peak, trough, peak. And when these two add together, you'll get nothing. They'll cancel each other out. That's destructive interference. And you can see this on the screen. It's a little bit brighter in the middle here. And then you can see that there's these lines that go off in these directions. And these lines are actually regions where there's destructive interference happening. So this is an interference pattern between two sets of waves. Water waves do this. Light waves do this. And you can change that pattern by changing the frequency. So if you make the drops happen a lot faster. So before we only kind of saw two lines. Let me make it a little brighter. Turning up the lights. I think I made the lines kind of move a little bit closer. Now there's one right there, one right there. I think you can make it even more pronounced by moving this. Yeah, separation. Putting them closer together. Oh no, I made it worse. Let me make it really far apart. Yeah, so you get now more nodal lines where you get destructive interference. And trust me, if you do the same thing with lasers or light, it does the same thing. I mean, this is computer simulation, but it does the same thing. So this is one of the reasons why we can treat light as a wave, because it behaves similar to the way water waves work. Now, if you have a slit, it does the same thing. So this is not a drip that's making these circular waves. You have a wave generator that makes these one-dimensional waves that just go kind of straight in one direction. Well, when they hit that wall with a little hole in it, they go from these kind of straight waves to spreading out radially. The light does this as well. If you take a laser and aim it at so laser, the way it works is you point at something, it just keeps going in that direction. It doesn't really spread out at all. At least not very much that we can measure too much. But if you point it at a very, very tiny hole, that light now starts to spread out like a cone shape. So that does exactly what these water waves do. And if you had two slits, not just one, you'll be creating an interference pattern again. Let me move this. So they radiate out from both slits, and it's kind of harder to see here, but you do get these little nodal lines, these little places where you get destructive interference. These patterns, this is a very simple pattern, just two holes. But let's say that you took a light source, turned it on, and aimed it at a hole that was round. Everything else is blocked. This is the diffraction pattern you get. We can start making that pattern a little more complicated. A little square hole, and this is the diffraction pattern you get as the light spreads out from the hole. It spreads out in this kind of pattern. You could make the pattern more complicated, two holes, and you get this pattern. I don't know if you can see it, but there's these kind of diagonal lines. So in addition to the larger features, there's smaller features inside. And you can get really nuts. So there's a more complicated pattern, and there's definitely some kind of interesting pattern. You can even go for like a little figure. And while this doesn't look like much to us, this pattern actually can be analyzed by a computer, and the computer can take this pattern and figure out what the original shape was. There are equations that model what happens. This is a big deal. In chemistry, we use this concept in something called X-ray crystallography. So we take a molecule and grow a crystal out of it, a perfect crystal where the molecule arranges itself in repeating patterns. And it doesn't even have to be a simple molecule. It can be a protein. It can be a piece of DNA. As long as you can get it to grow into a crystal, which is difficult to do, but you can do it. You make a decent enough sized crystal. You mount it inside the machine that uses an X-ray laser. And that X-ray laser will shine through the crystal. And because the molecule is literally atoms and stuff arranged in a certain pattern, kind of like this is, the X-ray will go through the atoms in the crystal and diffract off of it in certain patterns. And not just one image, but if you take that crystal and rotate it a little bit, take a picture, rotate, get a diffraction pattern, you rotate from all different angles, and you get a series of images. The computer can actually figure out exactly where those atoms are located. So if you've seen all of the structures of even the coronavirus spike protein, things like that, those images either came from X-ray crystallography, or there's other techniques as well, but X-ray crystallography is a big one. So just the simple diffraction, this concept of diffraction, you can do it on an atomic scale and figure out exactly where those those atoms that made that diffraction pattern happen. Okay. So that's a big deal. This is how we know light behaves like a wave. It just behaves like a wave, so we have to do it. But this wave theory of light is not enough. Because it doesn't explain black body radiation, which I kind of showed you what it is. And I'm not going to get into why it doesn't explain it too well, but it doesn't. It doesn't explain something called the photoelectric effect, which we're going to see. If you shine light on a piece of metal, electrons will come out sometimes. And it doesn't explain emission spectra. So I'm going to show you an emission spectra. So this is a little glass tube in a big plastic case. This glass tube is sealed. It's got hydrogen gas inside. And there's little electrodes embedded inside the glass on each side. And we can power them with this thing. So I'm going to stick it in this machine. There it goes. Turn it around. And if I turn on, it's going to apply a large voltage across those electrodes. And it's going to basically send a lot of energy into the hydrogen gas. And when it does that, come on. There's a bad connection somewhere. Did I short something out? No, that's correct. One second. There it is. There you go. So, turn it a little bit. There's this like pinkish light coming out. Now, pink is not a color of the rainbow. So, where is this pink coming from? It's actually a combination of a couple different colors. And hydrogen always gives this light, this color. Always. If I use a different element, like helium. Come on, helium. No, it's not working. Try it again. Oh, no. Maybe that's what it needed. There he goes. Here's helium. Kind of purplish white, mostly white. If anybody's ever seen neon before, this is a very classic 80s color. When neon lights were, I don't know, they weren't invented in the 80s, but they were very popular. Most neon lights are not neon. That's neon's color. They use other gases as well, just like the ones you just saw. And then argon, a little bit more purple. But where do these lights come from? The wave model of light does not explain this. This is what's called an emission spectra. So light is being emitted from matter. So how do we explain these colors? Where are these colors coming from? So we need to use a different model. We need to use a model that explains light as a particle instead. And these particles are photons. And we've already seen the equation to calculate it. That was our little preview. And the concept here is instead of So how do you relate the brightness of light to a concept of photons? So brightness in wave theory was the height of the peak, the amplitude of that wave. In the particle theory, a bright light means you have more photons. Not just high energy photons. That the energy of the photon is related to the wavelength of the frequency. But if you just have a brighter light, all it means is you have more photons. So, the wave theory of light, this was the main theory for a long time, till the end of the 19th century, so the 1800s. And they thought that the energy of light was only determined by the intensity of the light. It made sense. Brighter light means more energy, but that's not actually the case. And there's an experiment that proved that it wasn't the case. So Max Planck is the one who started out talking about or conceptualizing the existence of light as a particle. But it wasn't until, I think, Einstein who explained this effect, which was noticed by Hertz. Lots of famous names here. That's the guy who we named the frequency unit after. And this is the photoelectric effect. So let me switch to a different screen. I've got a Java thing pulled up. So what you're seeing here is a setup for the photoelectric effect. We've got a piece of metal right here on this electrode. And this metal is currently sodium. And we're going to shine a light onto that piece of metal. So I'm going to turn up the intensity of this orangish red light. So there's a 50% intensity. What does intensity mean? So don't forget, we just said that we're going to talk about intensity as numbers of photons. So now let's replace that bright light with photons hitting this piece of metal. And if I increase the intensity, you'll notice that the number of photons increases. It's just a torrential outpouring. Low intensity means very few photons. But nothing's happening. I'm shooting photons at this piece of metal and nothing's happening. Well, currently my light is set at around orangish red, 632 nanometers. And, whether it's really bright or low, doesn't matter. Nothing's happening. So if I start to reduce the wavelength, still nothing's happening. Till around, something's happening. So around bluish, maybe greenish, I'm getting these particles coming out of the metal. These particles are actually electrons, and they're mostly coming out kind of fast, but some of it, actually, the slow ones were from a previous wavelength that I had set it to and didn't wait long enough to see if something had happened. And they're still coming out. The faster ones are from this current light. And so basically there's like a threshold. There's like a minimum, or I should say a maximum wavelength before electrons come out for sodium metal. If I change the metal to something like zinc, suddenly nothing's coming out anymore. I mean, there's the leftover electrons, but nothing's coming out. For zinc, I have to lower the wavelength even further. And now I'm in the UV region. Nothing's happening. I've got to go way down here before electrons come out. So it's not a function of intensity. It's a function of the wavelength. So somehow a lower wavelength causes these electrons to leave. And Einstein was the guy who explained it all. He was like, well, light is photons, and these photons, the wavelength or the frequency of the light determines the energy of these photons, not the intensity. The intensity just tells how many. So for instance, if I were to, here, let me turn this a tiny bit down so they're going not too fast. So if I turn the intensity up, notice how many photons hit and notice how many electrons come out. So I turn the intensity up way high, and now there's a lot more electrons coming out. So the intensity just tells you how many photons are coming out, or you're hitting it with. And the more photons that are coming out, the more likely an electron is going to come out of that piece of metal. But whether it's bright or dim, if the wavelength is not the right energy, then no electrons will come out. I'm not going to play with this. That just plays with how accelerating and decelerating them. But that is the photoelectric effect. So basically, it kind of proved that intensity has nothing to do with the energy. All right? It was all the wavelength or the frequency. That affected the energy. Okay. So why is the electron only coming out sometimes? Well, we just talked about what an energy it takes to remove an electron, right? The ionization energy. Every atom has a specific ionization energy it needs to remove an electron. And so for sodium, it was a certain energy. That blue light was about the right energy to remove the electron. But when we switched to zinc metal, we needed a much higher energy. We had to shrink that wavelength all the way down to the UV region to get that electron out. So this is kind of important. make sure you understand the difference between the original wave theory of light and the more modern wave particle theory. So in the wave theory of light, we should predict that a bright light has more energy. That's incorrect now, but that's what the wave theory predicted. So it doesn't matter what color it was as long as it's bright. So if I have a bright red or a bright blue, according to wave theory, it doesn't matter. They both have the same energy. Again, this is incorrect, but that's what the wave theory predicted. So according to particle wave theory, when you combine them together, bright red light versus dim blue light, the dim blue light, it doesn't matter if it was bright or dim, it's the blue part that matters. Blue light has more energy. And whether it's bright red or bright blue, they're not the same at all. It's still the blue one that has more energy. Okay? So that's the big distinction. Okay. So yeah, this is one of the most famous things that Einstein did. It wasn't, I mean, yeah, he's known for E was equal to mc squared and a couple other things, but that was a big one. Okay. So let's kind of see what we can do with these concepts that we've learned so far. And this is going to be a little bit beyond what you guys can understand completely at the moment. But let me kind of introduce it as much as I can. So like I said, this is not something we have to learn specifically, but we're going to try to use the concept we know already to kind of predict something we don't know. So first of all, what is work function? Its work function is similar to ionization energy. Ionization energy is specific to one atom at a time. In fact, when we measure ionization energy, it's technically ionizing a gas phase atom. Work function is defined a little bit differently. You're still removing electrons, but you're removing electrons from a bulk material, so like a big piece of metal. That's the difference. And ionization energy, we tend to use units of joules for energy. And for work function, we're going to use electron volts, which is another unit of energy. That's it. Just energy still. And the conversion is right here. Electron volts are convenient because you get like bigger numbers that kind of easy to think about. And this table is full of work function values in electron volts. So here's the thing that's kind of beyond the scope of this class, but because this is what you'll study in 222. Band gap. What is that? If you're interested in semiconductors, band gap is where it's at. So I know you guys have studied metals versus nonmetals, and you guys know where the semimetals are, the metalloids. Another name for those metalloids, semimetals, is semiconductors. So what is a semiconductor besides being semiconductive? Well, more specifically, metals conduct electricity. So how does conduction work? They allow electrons to move freely through them. Okay? A material that can have electrons move very freely through them, that's a conductor. And that's what electricity is. Electricity is the movement of electrons. Now, a semiconductor is actually not something that is partially conductive. It actually is not conductive normally. So if I take a piece of silicon and I try to conduct electricity through it, it won't conduct. But a semiconductor is interesting because if I give it some energy, like heat it up maybe, it'll suddenly become conductive. So if you were an electronics person, you might be thinking that describes a switch. So it's not conductive, and then I do something to it, and suddenly it's conductive. That's what a semiconductor is. The band gap is the energy required to make it conductive. That's specifically what a band gap is. Now, how would you use this? What kind of advantage could you have? Well, you guys use this in your cell phones all the time. You got a camera. The camera sensor has to react to light. It's got to be able to say, oh, I got a signal when a certain kind of light hits it. whether it's visible light or infrared light. If you have night vision goggles, it needs to read infrared light. So the idea is, well, could one of these materials kind of switch on when it gets hit by red light? Right? So like I said, a semiconductor, you give it some energy and it's suddenly conductive. That's like a switch. So this is kind of the, this is a high level concept, but we're using stuff that we already know, stuff that we just learned to kind of answer this question. So why don't you guys try this? We're going to go to page 149, 150, and questions 2 through 7. And honestly, yeah, you're just going to use basic questions here. Or basic equations, I should say. So 149, 150, CTQ, 2 through 7. And I will be happy to walk around and start you off if you're stuck. The big clue is we are interested in energy. So maybe you should figure out what kind of energy that light has first. But I think it'll set you through it. We'll start with question 2 at least. Yeah. Let me see. How are we doing? Go through at least 4 or 5, hopefully. So the first few are good. I wanted to make sure you internalize the photoelectric effect conclusions yourself. We're going to go over in a second. I just kind of remembered. This is the PDB database. It's a free online thing that every research group submits all their structures to this thing for storage. And you can look up like anything. This is not. I don't think this is the coronavirus that is the one that's interested affecting us. But this was all of these positions of every single atom in here was determined using that X-ray crystallography technique, which is pretty precise. I mean, and so you can spin these around and see them. There's different visualizations. This is the space filling model, so the space the atoms take up. A more common view of like giant proteins is a cartoon structure, like this. If you take biochem, you'll learn what these are. There's the alpha helices and beta things. Anyway, just kind of showing you that these are alive and well. So, I'm just going to go through the answers really quickly. Hopefully you agree. And if you don't, and you're like, what's going on, let me know. So 2 observations, is subjective. Whatever observations you made is fine. But what is more critical in getting electrons to leave? It's the frequency, not the brightness. Recall that moving electrons requires light energy. What data suggests that about which is greater in energy, red or blue light? Well, only the blue light made electrons leave, so blue light must be higher energy. So this is kind of assuming you don't know this stuff yet. Do those results provide support for the wave theory or particle theory? Well, the wave theory predicts that bright light is where the energy is, and if bright light doesn't cause electrons to move, then it's got to be the wave particle theory. That's correct. So 6. There's a long explanation, but I kind of describe what the wave functions are, or not wave function, the work function is. So what trends do we see? Well, if you go top to bottom, especially over here, you can see that in general, and it's not perfect, but in general, it starts high and it goes down. It gets easier to remove an electron as you go down in the periodic table. You can kind of see that here. Like I said, it's not perfect, but you can see it. And then when you go left to right, as you go left to right, it gets harder to remove an electron. The energy goes up. You need to have more energy to remove an electron. It's not perfect, but yeah, in general, that's the trend. So what element will emit electrons in response to blue light if the energy of the photon is that? So what we need to do is calculate what that energy is for this blue photon in electron volts, so we can compare them to the chart up here. So if a photon has 4.42 times 10 to the minus 19 joules of energy, well, let's calculate that in electron volts instead. And I don't even remember what the conversion is, but if you look up in the previous page, 1 electron volt is 1.6022 times 10 to the minus 19 joules. And so that blue photon in part B, its energy in electron, anybody have that calculated? 2.76? Okay. I'll trust you. So that's the energy of the blue photon. Which metal could it eject an electron from? Well, pretty much none of these. These need higher than 2.7. So maybe barium, definitely cesium, strontium, rubidium, not calcium, definitely potassium, sodium. Oh, not sodium. Oh, sodium, yes, but not lithium. So a lot of these over here, but that's it. Those are the only metals that blue photon could ionize. And that's kind of what we saw in the simulated thing, on that Java applet. The sodium metal, you could get electrons to come out with kind of a blue light. But once we switch the zinc, Nothing happened. And that's because it takes a lot more energy to remove an electron from zinc. So going by that kind of concept, let's switch to semiconductor. Oh, you have a question?
No, sorry.
Oh, that's okay. Don't worry about it. Interrupt me if you need to. So we are making a CCD camera, which is basically the fancy name for what's in your phones. Although they have different names, the CMOS, things like that. But they all pretty much operate similarly. So if I need a material that will react to red light, what material is it going to be? Well, we'll have to convert the 650 nanometers into a comparable energy in electron volts. So 650 nanometers. First, let's convert that to meters. 1 nanometer is 10 to the minus 9. So that's 6.50 times 10 to the minus 7 meters. Let's now convert that wavelength into energy of a photon. So Planck's constant is 6.626 times 10 to the minus 34 joule seconds. Speed of light is 3.00 times 10 to the 8 meters per second. And this is the reason why we converted the wavelength to meters. They're going to cancel out with these meters. If you leave it in nanometers, it's not going to work. And so that energy is going to be e to the minus 34 times 3 e to the 8 divided by 6.5 e to the minus 7. 3.058 times 10 to the minus 19 joules. But that's not good enough. I can't compare joules to electron volts. Let's convert that energy to electron volts instead. It's just another unit for energy. I erased it. So 1 electron volt is, what was it? 1.602 times 10 to the minus 18? 19. Okay. So that number divided by 1.6022 times 10 to the minus 19, I get 1.9 electron volts. So that red light has this much energy, 1.9 electron volts. That is enough to trigger silicon. Silicon band gap, that's that energy to turn it on to make it conductive. So it's like a switch. Your circuit will sense, hey, something's hitting the silicon because the silicon's turning on. It'll work. It'll work with germanium too. But gallium phosphide is another semiconducting material that won't work with this. It's not enough energy. Hopefully I did this right. Did everybody get this number? Okay, good. And so now, there's, what if we wanted to do infrared instead? We wanted to make a camera that is reactive to infrared radiation instead. Remember, that's going to be a lower energy. Infrared is a shorter wavelength. It's going to end up, a longer wavelength, wrong way. It's a much longer wavelength. It'll end up being a smaller energy. And that small energy may not be enough to trigger silicon anymore. It may not be enough to trigger germanium. Maybe it is. So you have more limited materials that can detect something like infrared because it's such a low energy photon. It needs to be really sensitive. Do we want to do that one real quick, or let's probably skip that one? So, super advanced ideas. We can now use these basic concepts to kind of understand what kind of materials we need to make our sensors out of. So, all right. So don't worry about like the material stuff. Don't worry about that. Just understand how to go back and forth between different kinds of energy, different forms of energy, and understanding what the energy of a photon is, from its wavelength. We're going to be using these energy of the photons to help us understand how matter works, and this is just one way. Okay. Any questions on any of this? All right. So, here, you guys do this real quick. This needs to be, not hard to do. So, if you have gallium's work function, 4.2 electron volts, what is that energy in joules? And if you need a calculator, there's a bunch of calculators in that green bin. Just put them back before you're done. And I'm fine with the fancier scientific graphing calculators for quizzes and exams. I would just ask no phones or laptops. So we have those if you don't have one. Three answers. Come on. This is a one-step conversion. Okay. I'm going to reveal the answer. You're still working on it, no big deal. But we have a couple votes for C, one for A. So the answer is C. There we go. So should be a quick thing to do. Yeah, I don't expect you to memorize the electron volt conversion. I don't have it memorized either. But recognize electron volt is an energy. Joule is an energy. There should be a conversion you can look up to convert between the two. And there it is, one step. Okay. Now let's get to the prize, which is why we're learning about light. We want to look at how light interacts with matter. So we're going backwards now. Going back to Chemactivity 4. Or Chemical Inquiry 4, whatever it's called. So, why do certain compounds emit specific frequencies of light? So you saw those gas discharge tubes. You put energy in them, they emit different colors of light. I'm going to skip that for now. We'll talk about that when we get to quantum mechanics in a little bit. But so why do different elements and compounds emit only specific frequencies? So that's the goal to understand. Are they random or are they characteristic? So the hydrogen light that we saw, that pinkish light, it actually is a result of, and there's only showing 3 here, but it's actually 4 colors. The 4th one is pretty dim sometimes, so sometimes it's not included. But the 4th color is another in the violet region. So it's not here because it's usually very dim. But these colors combine to make that pink light that you saw. How do we get the spectra? Well, you take the discharge tube. It makes this pinkish light. You kind of shine it through a slit just to make a nice line so it's easy to see. And then you shine it through a prism. And if you've ever played with a prism, this glass, a triangular shaped glass, it splits white light into all the colors of the rainbow. So basically it diffracts the colors, or it refracts, refracts the colors. And different wavelengths will go through at different angles. So it splits the different wavelengths of light into different places. And what comes out are those 3, technically 4 lines, those 4 colors. There's only 3 shown here. And we're actually going to build one of these, not a prism, but we're going to build the hole detector, a way to measure the different wavelengths of light that is being emitted from something. So that's what we're going to do in lab this week. And then the next week, we're going to use it to do a bunch of experiments. So, hydrogen had that emission spectrum. if you look at the emission spectrum of other metals, you get different patterns. There's heliums, so two purples of blue, green, yellow, orange, and red. There's lithium, there's sodium, there's mercury. If you're in theater, you've heard of sodium lights. It's because they emit a really nice bright yellow color that kind of looks good. And that's why they use sodium lights. They emit that specific frequency. It looks better than fluorescent lights, put it that way. This is the continuous spectrum, but every element has its own little signature. And we can identify an element by the emission spectrum. This is how we know planets and suns are made of certain things. We look at the colors they emit, and we can tell what elements those things are composed of. Now, how do we explain this? Like, why do they make these colors? Well, first, we need to go back and kind of incorporate a new theory, and that is when matter absorbs light as energy, it doesn't absorb it any amount. Like, you can't give it any amount of energy and it will just absorb it. Matter will only absorb specific quantities of energy. And so that quantities part, that's the important part. So it's these specific quantities only. So you can get, so let's say the ground state, the lowest energy state of an atom is down here. Well, I can give this much energy to an atom, or this much, 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 and that's it. I can't do any amount. Like, it's not a rolling, sliding scale here. This is a more accurate representation of how atoms absorb energy in quantized amounts. So this quantized thing, that's where the quantum mechanics part, quantum, comes from. And so when it absorbs specific amounts of energy, it releases specific amounts of energy as well. So if you have a ball in a staircase, yeah, you could give it a ton of energy all at once, and it could lose all of that energy at once if you push it back down, or it could lose it in steps. It could lose this much energy, and then lose that much energy, two different amounts of energy. The same happens with atoms. Now we're going to use this kind of energy level kind of diagram to kind of explain how atoms absorb energy. And we're often going to show them as the electrons moving up and down, okay? This scale of energy. So when an atom absorbs energy, and it can absorb any kind of energy, whether it's heat or electricity, like in the case of the discharge tubes, or light, you can shine a bright light on it. It'll absorb energy any different way, and you can basically cause that electron to absorb any amount of energy, up to here, up to here, up to here, up to there, whatever. It depends on the energy. It can be pretty random, but remember, when you're dealing with a sample of atoms, and you're shining a light on a sample of atoms, there's like a trillion times a trillion times a trillion number of atoms. There's a lot of atoms in there. So the likelihood of an atom absorbing this much energy, or maybe this much energy, or they all occur. There's so many different atoms that everything occurs all at once. But let's say that this particular atom absorbs energy and it goes up to here. Matter doesn't want to keep energy. It wants to be in a low energy state. So it's going to want to get rid of that energy. When it gets rid of that energy, again, it could drop all the way down all at once. It could drop one step. It could drop 2 steps, 3 steps. It's pretty random. And remember, there's trillions of atoms. And let's say just a trillion of them have the electron in this state where it's absorbed this much energy. Some of them will drop down to here. Some of them will drop all the way down. It's a range of options, basically. They all happen. Well, when it releases that energy, it releases it in the form of a photon. Okay? There's a law of conservation of energy, just like there's a law of conservation of mass. When the atom wants to get rid of that energy, it has to get rid of it somehow. It doesn't just go away. So it's going to release that energy in the form of a photon. And so if the energy changes by this much, that change in energy, whatever it is going to go with the photon. And that's going to be the energy of the photon. And that energy is going to dictate what the wavelength of that photon is. And that's how we get these different colors and these specific colors. So, Bohr, Niels Bohr, that scientist I first pointed out in that picture, he is the one that came up with this equation, I think. Anyway, he's related to it. There is a version of this equation that is named after him. There's also a different version of this equation called the Rydberg equation. So, I don't know my history too much, but they both worked on it. What this equation does is model those quantized amounts of energy that a hydrogen, that any atom can absorb. Now, there's a restriction to this equation. It only really works well with hydrogen. Once you start using it with other atoms, it doesn't work as much. So you might be thinking, what's the point of it then? We'll get to that, okay? But what Z is the atomic number. So if we're dealing with hydrogen, that's going to be 1. If it's helium, it's 2. 3 for lithium, and so forth. N is we're going to call it an energy level. So this idea that an atom can absorb quantized amounts of energy, these different energy steps, these levels, we're going to call them levels, energy levels, are labeled 1 through infinity. They always start at 1. 1 is the lowest energy. And the next one is 2, the next one is 3, and so forth. These are the quantized energy levels that an atom can absorb energy at, okay? Now we can actually calculate the potential energy. You guys know what potential energy is. We calculated it with Coulomb's law. We can calculate the potential energy of an atom. Here's a new way to do it, using this equation. So if I have an electron in energy level 1, in a hydrogen atom, I'm going to plug 1 in here for the energy level, 1 here for the Z, calculate what is the potential energy of that atom currently. It's going to be a negative number, right? That's where this sign comes in. Right? Potential energy is going to be negative for an attraction. But then I could calculate, well, if the electron was up here at this energy level, what would be the potential energy of the atom? It's going to be higher. It's going to get closer and closer and closer to 0. Okay. So these are these energy levels. That N value, I called it the energy level. We're going to talk about it more specifically later on, but this is known as a quantum number. It is one of the quantum numbers we're going to study. Again, it starts at 1, and it steps in integers up to infinity. So how do you get the colors from hydrogen? So let's assume there's only 3, even though there's 4. The 3 colors you get are very specific transitions of an electron. What I mean by that is you've got an atom that has absorbed already some energy from the electricity, for instance. And let's say that the electron is in energy level 5 right now. If that electron drops to energy level 2, and this is I'm being very specific here, if it starts from 5 and drops to 2, that difference in energy is the perfect energy to make a violet photon. If it starts at energy level 4 and drops to energy level 2, then this energy is the perfect energy to make a blue-green photon. And then for the red photon, it's an energy level 3 to energy level 2 transition. Notice these are always going down. The energy is going down. So if you're losing energy, where is that energy going? It's leaving with a photon. The photon is leaving the atom, and it's taking that energy with it. None of these other transitions, like what about 5 all the way to 1? What about 4 to 1? What about 5 to 4? What about 5 to 3? All of these transitions are possible, and they all happen, but they do not give you visible photons. They give you infrared and ultraviolet photons too. Photons that are really high in energy, so they're ultraviolet. Photons that are really low in energy, they're infrared. These are the only ones that give you visible photons. And that's always this for hydrogen. So a transition can be an emission or an absorption. All right. In the case of these things, the absorption happens because of the electricity, and the emission is when the atom wants to give that energy back. It wants to get rid of it, dump it, and it dumps it in the form of light. Okay. So all the ways the energy starts the lowest, the electron starts at the lowest energy possible. Let's see if we get to that. Yeah. So we call that, yeah, we talked about this. Electrons can happen between any two energy levels. And all of these possibilities happen because there are just so many atoms that there is going to be some combination where that happens with a certain atom. All right, where is it? We didn't. All right, it's not here, but we'll get to it. There is a specific name for when the electron is in the lowest energy state possible. That state is called the ground state. For hydrogen, it's where the electron is at energy level 1, and that's it. That's the ground state. Any other state that the electron is in, it's in a higher energy state, we call that an excited state. So when you talk about the electron or the atom is excited, it's got extra energy, basically, that it doesn't want. And eventually, at some point, the atom is going to relax. That's a term we use. And it's going to emit that energy. It's going to emit that energy in the form of a photon. All right, so let's practice using that equation. Make sure it makes sense. So chemactivity 7, all right, I guess we're not going to go all the way back first. We're going to stay with chemactivity 7b, and we're going to do pages 155 to 157, CTQ 5 through 11. And if this is really difficult, I think we're going to have this as part of our lab as well. So we'll do stuff like this in the lab too, in case you need extra practice with it. to run too close to the end. I think everybody's tried some of these calculations already, which is good. If you're getting close to what I'm getting, you should be getting exactly what I'm getting, but something like that, you're good. So the model, it's just to let's go through the questions quick. Showing the relationship between energy and photon. What is the equation of the model showing? Oh, let's go to the. It makes more sense if I look at it. So there's the equation that shows the relationship between frequency and energy. I think that's what they're asking for. Yeah. So what in the model? It's this equation here. It's showing the relationship between energy and frequency. What is the equation showing the relationship between frequency and wavelength? It's right on the board too, but or it used to be. It's not there anymore. There it is. Frequency and wavelength. Frequency wavelength. This chem activity is using the correct, or the ones I like, the unit, the variable for frequency, because it was written by Jim Schneider, I think, who's actually the chair of the department right now. So there is somebody here that wrote some of this stuff. It's not all from another place. What is the equation that gives possible energies of the electron energy states in the hydrogen atom? Why are these energies negative? So that's this equation right there. Why are they negative? Well, again, we know from Coulomb's law that negative potential energies denote an attraction. And so they have to be negative. That's what keeps the electron on the atom. That's what's happening here. So it's crucial that we understood Coulomb's law and how you can think just pure particles, like how an attraction works, when you get closer, what happens to the attraction. When you use this higher charge, what happens to the attraction. Now we're going to keep that in the back of our heads, and we're going to use the Bohr equation to calculate these potential energies a slightly different way, but we can still understand what these potential energies mean, okay? That's kind of the whole point of going over Coulomb's law. So calculating the energy states. I did the first two already. Z for this particular atom is going to be 1 because we're dealing with the hydrogen atom. If it's not a hydrogen atom, plug in whatever the atomic number is. Don't forget that. N is going to be the energy level. So if we want E1, that subscript was an N, we're talking about N is equal to 1. E2, N is 2. Don't forget to square it. I'll do one real quick. E3, very simple, minus 2.178 times 10 to the minus 18. We're going to do 1 squared on top because it's still hydrogen. 3 squared on the bottom. And what's this going to be? 178 minus 18. It's just mostly, once you get used to it, it's like tedious. And if it gets tedious, you're in a good state. You're like, hopefully you understand this well. Okay, so that's E3. You could do E4, energy level 4. But these are purely potential energies. Like, hey, the atom has this energy currently. Now, we actually don't quite care about the current potential energy. And we don't really care about the future or past potential energy. What we care about is the change. So how did the atom change in energy? So for instance, if you have an atom that had an electron in energy level 2, and then an electron drops to energy level 1, we care more about the change in energy. Like what is that difference in energy? Because that energy has to be emitted as a photon. So we care about the change in energy. So the difference in energy, this delta, this triangle thing is a Greek letter delta, capital delta. There is a lowercase delta too. And there it is. It's the final energy minus initial energy. That's what the change in energy is. I think that's not quite right, but we'll talk about why that is. What's on this board here is not quite what's on the screen is not quite right. So let's go with what I wrote. Change in energy of the atom is the final energy minus the initial energy. So in problem 9, we're talking about an electron that started in energy level 2. That's the initial energy. It started at energy level 2, and it transitioned to energy level 1. The final energy state was energy level 1. So the change in energy is going to be E1 minus E2. So far so good? So I'm going to plug those in. E1 is minus 2.178 times 10 to the minus 18 joules, minus a minus 5.445 times 10 to the minus 19. I'm sorry if I'm writing small. That's the change in energy. And so if I calculate that, don't, be careful of the signs. A minus and a minus becomes a positive. So negative 2.178 times 10 to the minus 18 plus 5.445 to the minus 19. I get negative 1.6335 times 10 to the minus 18. So what does this mean? There's a negative sign here. That is the difference in energy for the atom. A negative change in energy means the atom has lost energy. That should make sense, right? If the electron was at a high energy level and it drops to a low energy level, the atom is emitting energy. It's getting rid of some energy currently. That's the energy it has lost. It lost 1.6335 times 10 to the minus 18 joules. Where did that lost energy go? That lost energy was carried away by the photon. So the photon had that missing energy. The photon has a positive 1.335. If I can write numbers properly. Times 10 to the minus 18 joules. Does that kind of make sense? So the atom lost energy. Where did it go? It went with the photon. So the photon is emitted, flying off, taking that energy with it. So, is the energy absorbed or emitted by the electron? Well, the energy is emitted by the electron. The electron is losing that energy. And it's emitting it in the form of a photon. So that's a more accurate explanation of instead of what's on the screen there, or what was in the little equation box. So now that we know the energy of that photon, what color is it? What's the energy of the, we did 9 and 10, sorry. So we just calculated the energy of the transition. It's a change of 1.6335 times 10 to the minus 18. It's an emission. And that's the energy of the photon that is emitted. Okay? So 11, now let's determine the wavelength of that photon. So I'm just going to take my trusty equation, energy of a photon. I can convert that to wavelength. I'm going to manipulate this, solve for wavelength instead. Planck's constant times the speed of light divided by energy. 6.626 times 10 to the minus 34 joule seconds. Speed of light is 3.00 times 10 to the 8 meters per second. Divided by that energy, 1.6335 times 10 to the minus 18. Now, if you get confused by the signs, oh, it should be negative, it should be positive, just remember that your photon energy can never be negative. If you plug in a negative here, you'll get a negative wavelength, which won't make any sense. So photon energy is always positive, okay? So our wavelength is 6.626 e to the minus 34 times 3 e to the 8 divided by that number 1.22 times 10 to the minus 7 meters. Well, what is that in nanometers? Since nanometers is the language for visible light, if we wanted to use to figure out where it is. That's not necessary, but let's do it anyway. 1 nanometer is 10 to the minus 9 meters. So we end up with 122 nanometers. That's not visible. Visible is between approximately 400 and 800. This is well below 400 nanometers. Is this infrared or ultraviolet? Ultraviolet, yeah. Shorter wavelength means higher energy. So this is shorter than violet, so it's ultraviolet. So one of the transitions coming from that pink light that I turned on earlier is some ultraviolet light. Now there's a coating on the glass, so it's blocking a lot of the bad light. But that's one of the forms of light that is emitted. We could probably do plenty of other calculations. You know, we can do a 4 to 3, we can do a 4 to 2, we can do a 3 to 1. There's the combinations are innumerable. But only some of them are going to be visible. The rest are going to be ultraviolet, too high energy, or too low infrared. But notice that this equation, it doesn't change for hydrogen at all. It's always 1 here for hydrogen, and the only other thing you plug in is an energy level. So hydrogen, if we can believe this equation, if we we assume that it works perfectly, hydrogen's always going to give those same energy levels. And that's why it doesn't matter what sample of hydrogen you have, it's always going to emit that pink light. It's going to create those 3 colors that mix together to make that pink color. Helium does the same thing, and so forth. Now, I mentioned that the Bohr equation doesn't work very well with atoms other than hydrogen. So we're going to get to this, but once you introduce an atom that has more than 1 electron, so if you have helium, for instance, that has 2 electrons, that complicates things. Because not only do you have the electron nucleus attraction, you have electron-electron repulsion. So just adding an extra electron complicates this equation quite a bit. So this equation doesn't work very well for plain helium. It does work really well for helium plus, helium that has only 1 electron left. And any weird atom that only has 1 electron, lithium 2+, works pretty well with. Actually, weirdly, it works fairly well with everything from group 1. So there's a clue as to the structure of what electrons are doing in an atom. Like potassium, which has 19 electrons in it. Even though there's 19 electrons, this equation works okay with potassium, despite all the electron-electron repulsions complicating everything. So we're going to get into that, dilemma. Why does it work, even though there's all these electron-electron repulsions happening? So we're going to explore that. We're going to get into it. We're going to keep building up our model of the atom. It's way more complicated than just this. This is the first step. We're going to get energy levels. We're going to find sub-levels. If you did chemistry in high school, you might have learned it as shells and subshells. And we're going to understand the whole concept behind electron configuration, all that stuff. So that's what you have to look forward to in this class. All right. I'll stop there. Let's see what's on the slide just to make sure. Yeah. All right, we're done. All right. Let me know if you have any questions. We can talk before or after. If you got your quiz back and you don't